Good morning, everyone. Welcome back to my channel. Today we'll be talking about the fourth lecture of this series of what machines. So in today's videos, we'll be discussing equivalent circuit, right? Equivalent circuit of a transformer is what we'll be discussing today. Now, looking at the diagram before us, we have what the complete equivalent circuit of a transformer. Then we have what the equivalent circuit when referred to the primary side. These are the things that you will have. Equivalent circuit when referred to the primary side. Then we have what equivalent circuit when referred to the secondary side. So this is what we'll be discussing in this video. So stay tuned and don't forget, after watching this video, it's still better you read through some textbook to have what a better understanding of what the explanation, because definitely I won't want the video to be too long. It means there are some things that I won't be able to mention because of time. But going through our textbook like engineering technology by BL and BK Teraja and some other what textbook, we definitely would simplify the work more. So let's go. Now we already know what is a transformer, because in our previous video we have already given what definition of what and definition and meaning of what transformer. And also again, a transformer is a static electrical machine used to transfer electrical energy from one AC circuit to another what AC circuit through electromagnetic induction. So it means the both side of what a transformer, the input and the output, they are all what AC circuit. And definitely we know this transformer to be what a static electrical machine, right? It's called a static electrical machine because it does not have what a physical moving part. Yes, that is what I would call it. It does not have what a physical moving part. That is what I call it, a static electrical machine. Then in practice, definitely we know transformers are not perfect. There's no machine that is perfect. Some losses must be incurred. Therefore, transformer cannot be represented as an ideal device only. Even when we are talking about ideal transformer, we talk about there's no copper loss, there's no core losses, no iron losses. But in real sense, in reality, there must be losses in transformer, because even when you are using your transformer, you see, because with time it becomes hot. So definitely that heat that is generated is as a result of what losses in the energy or the electrical circuit. And also in the hysteresis, the magnetic field, there are also losses. So it means there is need to discuss the equivalent circuit of a transformer, which will give you what the real model, the real behavior of what a transformer. So the key idea of today's class is what the equivalent circuit of what a transformer help us to analyze the following. One, with the help of what equivalent circuit of a transformer, you will be able to calculate what voltage drop across what is transformer, both at the primary side and what at the secondary side. And also with the help of what equivalent circuit of transformer, you won't be able, or you should be able to calculate what copper losses. And don't forget, we say copper losses is mainly what I square R losses, and this may occur at the primary and also at the secondary side. So it means copper losses occur at the primary and what the secondary side. So if you want to get what the total copper loss, you have to sum the copper loss at the primary and what at the secondary side. And also we have the core losses, which normally occur at what the shunt side of the short part of what the transformer. And also we have what efficiency. The efficiency of a transformer is not 100% efficient. Since there is losses, then it means the efficiency should be below what 100%. Then we have voltage regulation. Also with this what equivalent circuit of transformer, you should be able to calculate what voltage regulation. And also we have short circuit and what open circuit test results. And also with this equivalent circuit, you should be able to still calculate that. Now review of an ideal transformer. The normal assumption we normally make about a transformer is that a transformer has what? Zero winding resistance, which is not possible. Those are just assumed when we want to solve or when we want to make what the situation very easy and more comfortable. But in ideal situation, there must be winding resistance. So in ideal situation, we assume there's no winding resistance, so the zero winding resistance. And also in ideal situation, we assume no leakage flux. Even when we know there some fluxes must leak, it's not the total flux that is generated that is being linked with what? With the secondary winding. And also no core losses. Yes, these are some of the what the ideal factors we do consider to be ideal. No core losses, and also infinite core permeability and 100% efficiency. We know with those six items we have listed, zero winding resistance, no leakage flux, no core losses, infinite core permeability, and 100% efficient. These are just what? Assume, they are just assume. It means it's not even possible. So for a real transformer, or what transformer in practical, in reality, then definitely those things are not what possible. But normally these are some of the things that what are assumed in transformer in ideal state. Now, voltage and turns ratio. We have already talked about what is voltage ratio. We said voltage ratio is what the primary voltage is the ratio of what the primary voltage to the secondary voltage, or our number of turns at the primary to the number of turns at the secondary, which should definitely give us what our turn ratio. And we know this turn ratio is same as what, I think there's a error here. Okay, yeah, it's correct. We have one all of our turns ratio to be what? The primary current divided by what? The secondary current. So it means if I'm imputing my current ratio here, this should be equal to what? I2, the current at the secondary, divided by what? The current at the primary, which is the same thing as this. So the current at the primary divided by what? The current at the secondary is 1 all over what? Our turns ratio. Then from here, it means what? My I1 equals what? My I2 divided by what? My alpha. So let's go. So practical what? Transformer. The transformer in reality. So in real transformer, the following effect must be considered. Must be considered. You don't have to assume them. Number one, winding resistance. Winding resistance, both at the primary, at the secondary, and at the shunt part of what the transformer. Winding resistance are there. 2. Leakage reactance. 3. Core loss. And 4. Magnetizing current. Right? Magnetizing current. These practical effects are represented using resistances and reactances in the equivalent circuit. These are one of the reasons why we decided to go and discuss about the equivalent circuit of what? A transformer. Now, component of transformer equivalent circuit. The main component, the major component we have in transformer equivalent circuit, there are main four. The four are: one, you have what? Winding resistance, right? So in the winding resistance, you have primary winding resistance and you have secondary winding resistance. That is one. Two, you have what? Leakage reactance. You have primary leakage reactance and you have secondary leakage reactance. That is two. Three, you have core loss resistance. And the fourth one is what? Magnetizing what? Reactance. Right? Don't forget this core loss resistance and magnetizing reactance. These two parameter forms what? Our shunt part. So let me take us back to the shunt part. So this is this part, right? Is this part. This part is where we have what? Our core loss resistance and what? Our magnetizing reactance. Now, primary winding resistance. The primary winding resistance is made up of copper. Don't forget, your winding is mainly made up of, it's either copper or aluminum. Normally, aluminum or copper is better. However, it's too expensive. It's expensive compared to what? Aluminum. So in some transformer, you will see them, they will use what? Copper. definitely that should be what more expensive. Why some they tend to use what aluminum. Now, whichever material they use, either copper or aluminum, definitely it should be having what resistance, right? Since every conductor have resistance, the primary winding has resistance also. Then this resistance is what leads to what copper losses. So it means at the primary side we have what the primary current square multiplied by what my primary resistance. It will give me what the copper loss at the primary side. Then also at the secondary side we have what the current at the secondary winding square multiplied by what the resistance at what the secondary winding. Then it will give me what the copper loss at what the secondary. Then now for the total copper loss in the circuit will be what? The copper loss at the primary plus the copper loss at the secondary. Then we also have what? Leakage reactance. We know that not the entire flux that is produced by the primary winding is linked with the secondary winding. Some flux will definitely be what we escape. This flux, this is called what? Primary leakage flux. So those flux that did not link with the secondary coil, they are what? The leakage fluxes. So these leakage fluxes will produce what? Leakage reactance. And we know our reactance will be what? 2 per FL, right? Then at the primary, the reactance at the primary, then it means what? We'll be dealing with what? The primary what? Inductance. Are we there? Then we have what? X equals what? WL, and our W, which is what the angular velocity, is usually represented by what? 2 per F, where our F is what? The frequency. So we also have what? The leakage reactance. So at the secondary winding, we also have what? Our what? Inductance there, secondary what? Inductor. So it means what? Our X will be what? 2 per F L2. Leakage reactance causes voltage drop and affect the voltage regulation. So because of what this leakage reactance, it will make the voltage, the normal voltage that was supplied to the circuit, to drop a little bit, right? So because of that, we have effect. Then because of that, it will affect what the voltage regulation. Now the core loss resistance and the magnetizing what? Reactance. The transformer core is responsible for carrying the magnetic flux. Two important currents are associated with the core. We have already explained what the core is, right? We said the core is the part that what the magnetic flux tend to pass through. The core, right? Then this core is associated with two things: the core loss current and the what? Magnetizing current. Which is this? Because as you can see, this is the shunt part of what? The transformer. And definitely whichever current that is coming here, which is the core, whether you call it IC, right? Call it IC, the core current, but then it will split between this. So we have what? The core loss current. The core loss current is the current that flow through the what? The core resistance. And we have what? The magnetizing current, which will flow through what? Through the inductor, right? These are represented by what? A short branch in the equivalent circuit, as we have what? Explained earlier. So core loss resistance. The transformer core has iron losses, and these iron losses is splitted into two parts, or the two losses that form what? These iron losses are what? Hysteresis loss and eddy current loss. So it means iron loss uh, is broken into two parts. Hysteresis loss, which will be as a result of what? The magnetization here, or by what? The magnetic field or the inductor here. And also we have eddy current loss as what is a result of what? The resistance then. So these losses are represented by a resistance called the core loss resistance. So the core loss current is, we have IC equals V1 divided by what? RC. Our V1 is what? The primary what? Voltage. So the core loss power, now the power loss in the core is what? Pi, or you can call it what? Iron loss also, is V1 square over what? RC, and which was gotten from here. From here, when we have what? Our V equals IR, Then if V equals I arrow and you're looking for power, we know our power to be what? IV. Then you can decide to remove your I because we have P equals IV, right? You can remove your I and represent it with V. Then it means you have V1 all over arrow S, then multiply by what? V1. So V1 times V1 give what? V1 squared. Then it means we should what? Have this as what? The core or iron loss. Then the next is what? The magnetizing reactance, which is what? Xm at what? The shunt winding. So the magnetizing reactance represents the current required to produce the magnetic flux in the transformer core. Then definitely this magnetizing reactance is what is responsible or is bear with the responsibility of producing what? The magnetizing flux in the transformer. Definitely, if there is no magnetizing flux in the transformer, then it means the secondary winding won't be able to cut any flux. Now, our magnetizing current is Im, which will give what? Our V1 divided by what? Our Xm. So the no load current is a phasor sum of core loss current and what? The magnetizing current. So our no load current, which is what? IO, is the core loss current. Don't forget, we said the core loss current is the current that is passing through what? The resistance, the shunt resistance. While the magnetizing current is the current that is passing through what? The shunt inductor. So our core loss, our iron, our no load current is what? The core loss current plus J of what? The magnetizing current. So if I decide to remove my J, it means I should be able to square both sides. So we have what? My core loss current to be what? The root of what? IC square plus what? IM square. So exact equivalent circuit of what? A transformer. So there's also need to discuss the exact equivalent circuit. Now when we are talking about the exact equivalent circuit, this is what we now say refer to the primary or refer to the secondary. Because before we have been talking about the total equivalent circuit of what? The transformer without referring to any particular side. But in our discussion now, we will be referring to a particular side. So the exact primary circuit includes one. To the primary side, we have R1 plus JX1. To the secondary side, we have R2 plus JX2. Then at the shunt branch, we have ROC, which is parallel to what? To JXM. So the short branch is placed across what? The induced primary voltage because it represents the core behavior. Now, description of what? Exact equivalent circuit. We already know this. My R1 represents your primary copper loss, X1 represents primary leakage flux, R2 represents secondary copper loss, X2 represents secondary leakage flux, down to what? Our Xm. So referred equivalent circuit. For easy analysis, transformer parameters are usually referred to one side. Either you are referring to the primary side or you are referring to the secondary side. Now it means the main reason why, okay, let's say you are referring to the primary side, then there are some components at the secondary side that will definitely affect your calculation at the primary side. Let's assume when you are calculating, let's say the transformer is on no load, right? On no load. Now, since the secondary is not connected, because when you say on no load, it means the secondary is open circuited when the primary is connected to the source. So when the transformer is running or working on no load, then that secondary current, the resistance at the secondary, will also affect the primary current and the resistance and the total resistance at the primary, because the resistance at the primary is what is responsible for the voltage drops and the total current that will be in the circuit. So because of that, there is need for we to discuss what equivalent circuit when referred to each side of what? The transformer. This removes the ideal transformer from the circuit and allows normal circuit analysis. Now, equivalent circuit refer to the primary side. As you can see in our diagram, this is an equivalent circuit when referred to the primary. Now, as you are referring to the primary side, the things that you will be seeing are, you have R1, you have GX1, you have R2, but you have been referred to the primary now. You have JX2, but you are referred to the primary, and you have the secondary current referred to the primary and what is primary current. And also you have what the load inductance when you refer to the primary side. So our secondary current when referred to the primary is A square, that is turn ratio square, R2. Then our secondary inductance when referred to the primary is also what, turn ratio square, X2. Then our load when referred to the primary is also what we call it what, load impedance, is turn ratio square multiplied by what, our load. And we know our turns ratio to be what, N1 all over what, N2. Then you also have what, the representation of those things on our circuit, where our ROC is the core loss component, while our XM is what, the magnetizing what, reactance. So let's continue. The total equivalent resistance referred to the primary side is this. So you see the total equivalent resistance referred to the primary, we have what, R01. So this is what the equivalent resistance, right, when referred to the primary. So it means for the primary side, we have what, R1, the resistance at the primary, plus the resistance at the secondary when you refer it to what, to the primary, right? The resistance at the secondary when you refer it to the primary. So we have what, R01 to be what, R1 plus A square R2. So the secondary resistance when referred to the primary is what, A square R2. Then the total equivalent reactance referred to the primary side is X01. We have X1, the reactance at the primary, plus the reactance at the secondary when referred to the primary. Then this is what the formula to denote it. And also the total equivalent impedance when referred to the primary is what, Z01, which is R01, the equivalent reactance, the equivalent resistance referred to the primary, which is this, plus the equivalent reactance referred to the secondary, referred to the primary, which is this. So now equivalent circuit referred to the secondary. Now it means the same thing we have done to the primary is what we'll be doing to the secondary also. Now our primary resistance referred to the secondary is R1 divided by what, our turn ratio square. And also for our primary inductance referred to the secondary, which is what, X1 prime, is what, X1 divided by what, turn ratio square. So this is what the equivalent circuit referred to the secondary. It means we'll be having our R1 prime, our JX1 prime, our I1 prime, then our R2 and X2, and also I2. And this is what the shunt branch of what, the circuit. Now we have what, our V1 prime to be what, our V1 divided by what, our turn ratio. Don't forget, the V1 prime is the primary voltage referred to the secondary, right? So it is also, we have what, our current. Now our equivalent or total equivalent resistance referred to the secondary, we have R2 plus R1 prime, and we know our R1 prime to be what, R1 divided by what, A square, that is turn ratio square. So equivalent circuit referred to secondary continue. Our reactance is 02, X02, which is what, the reactance at the secondary plus the reactance at the primary when referred to the secondary. So this is noted by this. Then so the impedance is this. So approximate equivalent circuit. For many practical calculations, the exact equivalent circuit is simplified. The short branch, which is this, is moved to the input terminals. Yes, this gives this gives an approximate equivalent circuit that is easier to what analyze. Why is this approximation acceptable? The approximation is acceptable because the no load current of a transformer is usually small compared with the full load current. Therefore, the voltage drop in the primary resistance, the primary resistor and primary reactance due to no load current is small. So in the simplified equivalent circuit, the short branch may even be neglected for load calculation. Yes, see, in most of our calculation, when you are talking about equivalent circuit, the short branch of the transformer is not mainly shown. You hardly see it. So then the transformer is represented mainly by what? R equivalent plus JX equivalent. And our Z equivalent is what? Our R equivalent plus JS what? Equivalent, which is this. This simplified circuit is used for calculating our full load voltage drop, our core loss, our voltage regulation, and also open and short circuit current. Now we'll be discussing what? The phasor representation, phasor interpretation of the equivalent circuit. So the equivalent circuit can also be understood using phasor. For a lagging power factor load, the secondary terminal voltage is less than the induced voltage, right? For a lagging power factor. This is because of what? Voltage drop across resistance and leakage reactance. And don't forget, the power factor is usually lagging because of what is what? Inductive in nature. So the voltage drop at the secondary is I2, the secondary current, multiplied by what? My equivalent current at what? The secondary. And also I have what? My I2 x02. So the approximate secondary induced voltage, which is what? E2, is the terminal voltage at the secondary plus my I2 open bracket this, and this is responsible for, this is what? The voltage drop across what? The secondary terminal. So the induced voltage equals my terminal voltage plus my voltage drop. So for lagging power factor, my induced voltage is approximately what? My terminal voltage plus the voltage drop. So voltage regulation using equivalent circuit. The voltage regulation is the change in secondary voltage from no load to full load, expressed as the percentage of what? Full load. So here we have what? Our voltage regulation to be the induced voltage minus the terminal voltage divided by what? The terminal voltage multiplied by what? Our 100 to convert it into what? Percentage. So using approximate equivalent circuit, we have this, that because we have already seen that our induced voltage minus terminal voltage will give us this. So let me take you back. Because here we have what? Our E2 equals this, right? Then if I tend to move this to this other side, so this will remain. It means I will have what? My E2 minus V2 equals this. And that is what we are using on what? This circuit. So it means this is same as what? This. Then for leading power factor, now note it, for lagging power factor, this is a plus sign, but for leading power factor, this is what? A negative sign. And don't forget, for a lagging power factor, it means it's inductive, so the inductance is always positive. But for a leading power factor, which means the circuit is what? Capacitive, then it means the capacitor is always 1 all over. So it means it should be what? Having a negative sign here. So this is what the voltage regulation for lagging power factor for inductive circuit, and for leading power factor for what? A capacitive circuit. So losses represented in what? Equivalent circuit. So for our copper loss, we have this. We have I square, which is what? The total current in the circuit multiplied by what? Our R equivalent. At full load, it will be what? The full load current square multiplied by what? Our equivalent what? Resistance. at fractional load, then it will be what? The fraction of the load of the current, the fraction of the current square multiplied by what? Your copper loss at full load. So core loss. Core loss occurs in the iron core and is almost constant if voltage and frequency are constant. Definitely, we say our core loss is occurring at what? The shunt part of what? The transformer. So we have our core loss, or you call it what? Our iron loss, is what? V square equals what? The resistance at what? The core, the shunt resistance, short what? Resistance. So core loss is obtained from what? The open circuit test. Right? Is during the open circuit test you calculate what? Your core loss, because we have already given, let me take you back, because we said our no load current is what? The core. Yes, look at it here. We said the no load current is the root of what? The core loss current plus our what? Plus what? Our magnetizing current square. So it means during the what? The open circuit test or at no load, that is when you can what? Calculate what? Our what? Core loss current. So let's move forward. Yes. Now efficiency using equivalent circuit. We know our efficiency to be what? To the output, to be what? Output power divided by what? Input, then multiplied by what? 100 to make it what? In percentage. So our output all over, we know our input to be what? Our output plus losses, right? Our output plus losses. And we say we have two losses in transformer. We have the iron loss, also known as what? The core loss, and we have what? The copper loss. Then it means our losses will be what? Iron loss plus copper loss. So our output is same as what? The voltage at the secondary multiplied by the current at the secondary, then multiplied by what? Our power factor. Then divide by our output, which is this, then plus what? The losses. So now open circuit test. The open circuit test is used to determine the shunt parameters of what? Our transformer, because we said it's during the open circuit that is where you will be able to what? To calculate your what? Your core loss current and what? And the magnetizing current. The core current, yes, core loss current and what? The magnetizing current. And usually the low voltage side is supplied while the high voltage side is what? Left open. It means the primary side is supplied or is connected while what? The secondary side is what? Open. So the measured quantities are what? Open circuit voltage, open circuit current, and what? Open circuit power. So calculation from the open circuit test, we have what? The open circuit power factor will be open circuit power divided by what? Our open circuit voltage multiplied by what? Our open circuit what? Current. While core loss current is what? IC multiplied by what? Our open circuit current multiplied by what? The open circuit power factor. And magnetizing current, which is IM, is what? Our open circuit current multiplied by what? Sine of what? This. Then core loss resistance is RC divided by our open circuit voltage divided by what? Our IC. So magnetizing reactance is what? Our SM equals our open circuit voltage divided by what? Our magnetizing current. Now the other test is what? Short circuit test, because we say normally we have two types of tests in a transformer: the open circuit test and what? The short circuit test. So the short circuit test is used to determine the equivalent series resistance. Now we say for the open circuit test, we use it to determine the equivalent circuit of what? The shunt parameters. Yes, the parallel part of the part, which is what? The magnetizing what? Part. And also for short circuit test, we use it to determine what? The equivalent series parameters. So usually the low voltage side is short circuited and reduced voltage is applied to the high voltage side until rated current flows. Now the measured quantities are the short circuit voltage, short circuit current, and short circuit what? Power. So the equivalent impedance are what? The Z equivalent, which is what? The short circuit voltage divided by what? Our short circuit current. Our equivalent resistance is what? R equivalent to what? Short circuit power divided by what? I square short circuit what? Current. The equivalent reactance is what? Our X equivalent equals root Z equivalent square minus R equivalent square. So short circuit power represent copper loss at the test current. So a transformer has the following parameters. We are told to solve this. Our R1 equals to 0.5 ohms. Our X1 is what? 1.2 ohms. And R2 is what? 0.02 ohms. And X2 is what? 0.05 ohms. And our turns ratio was given to be 10. We are told to look for what? Sorry. We are told to calculate for what? Our equivalent resistance at the secondary refer to the primary. Then also the equivalent reactance at the secondary refer to the primary, and also our equivalent primary side reactance resistance and equivalence primary side what reactance. Now in solving that, we have what? Our secondary resistance referred to the primary to what? Our turn ratio square multiplied by what? Our secondary resistance, which our turn ratio is 10 squared, then multiplied by what? Our secondary resistance, which is 0.02. Then you multiply them, it will give us 100 multiplied by 0.02, which is what? 2 ohms. Then we have what? Our secondary reactance referred to the primary to be what? Our turn ratio square multiplied by what? X2. Then we put the value here. 100, we have 100 multiplied by 0.05, which is this. Now the equivalent resistance referred to the primary give what? My primary resistance plus my secondary resistance referred to the primary. So my R1 was going to be 0.5. My R2 prime is now what? 2. So it means I should have what? 2.5 ohms. My equivalent reactance referred to the primary will give me what? My primary reactance plus my secondary reactance referred to the primary. So my X1 was going to be 1.2, and I will have what? My X2 prime to be what? To be 5. So it means I should have what? 6.2 ohms, right? Now an open circuit test gives this. My V naught is what? V output. V no load is what? 220 volt. I no load is what? 2 amps. Then the power at no load is what? 100 watts. I was told to find no load power factor, call loss current, magnetizing current, which is C and what? XM. No, I was told magnetizing current, right? And don't forget your magnetizing current is what? IM. So from that we have our solution. Our power factor at no load is what? P0, which was going to be 100, divided by what? My no load voltage and no load current, or open circuit voltage and open circuit current. So we have what? 100 multiplied by what? 220 multiplied by 2, which will give me 0.227. Then from here I can get what? My angle. So my IC, which is what? My core loss current. My IC equals what? I no load cos power factor, right? So I have what? My I naught was given, then my power factor is what? 0.227. So I have this, right? What my IM is I no load sine this. Then before I can get this, so it's either you take this route, or you can just from here take the, let's say this angle inverse will give this angle will give me what? Cos inverse of this. So once you look for the cos inverse of this, then it means I will have what? My IM equals what? My I naught is 2 multiplied by what? The sine of theta, which is this. So it means I should have what? 1 point this. Then my RC, because I was told to calculate what? The magnetizing current, my IC, right? So my RC is what? My V no load divided by my what? My IC, which is my V no load is what? 220 divided by my IC was given to be I think I got my IC. Yes, 0.454, which is it. So it means my RC is what 484.6 ohms, while my XM is V naught all over what my IM. My V naught is 220, and my IM is I've gotten my IM. Look at my IM. My IM is what 1.948. So I have this 220 divided by 1.948 equals to 112.9 ohms. So summary of what our today's class is that the equivalent circuit of a transformer is a circuit model that represents the real behavior of what a transformer. It includes winding resistance, leakage reactance, core loss resistance, and magnetizing reactance. Now, by using this circuit, engineers will be able to calculate transformer efficiency, voltage regulation, losses, and performance under different load conditions. So this is the end of our class, but we have some what question that you should play with. Just try, you can pause the video so that you get what the questions. Try to play with those questions, at least solve them. Once you go through the video very well, then solving this question won't be what a problem. Then we have another set of what questions here, and say thank you for listening and thank you for watching. So we have come to the end of this video. Bye, and don't forget, Spark Scholar from idea to paper. Bye, and have a nice day.